Ladies and gentlemen, we have a wonderful visiting delegation from Beijing, from the Beijing University of Chemical Technology, and we're hoping to introduce new interactions both at the undergraduate and research level, with graduate student exchanges, undergraduate exchanges, and our two universities are very well matched from the description of each of our universities. We're both very young universities, young researchers, interested in chemistry and nanotechnology, material science, engineering. A wonderful match, actually. And my colleagues who I met for the first time today are wonderful individuals, and it's a pleasure to have been discussing research and possibilities with them. So today, very kindly, we have Professor Jing, who is the director of State Key Lab of Chemical Resource Engineering, and a distinguished young scientist supported by the NSFC in 2009. Professor Jing received her degrees in BSc 1988, master's degree in 1991 from Peking University in China, and PhD degree from Beijing University of Chemical Technology in China in 1999. She was promoted to full professor in July 2001. She has been a visiting scholar in several universities. For example, the University of New South Wales in 1996, the University of Oxford in 2003, the Max Planck Institute for Recruiting Forschung in 2006. Her research is focused on catalytic materials and environmentally friendly catalysis. Over 130 peer-reviewed papers and 20 patents have resulted from her research. A very prolific researcher indeed. Two projects in which she has participated have been awarded prizes at the national level. In 2002, she was awarded the title of Outstanding Key Teacher by the Ministry of Education. In 2004, she was selected to participate in the New Chemistry Outstanding Talent Scheme of the Ministry of Education. And in 2010, she was supported by the National Science Foundation as a distinguished young scholar. And Dr. Jing will be presenting her work on the intercalation of chiral ligands to make impacts on transition metal asymmetric catalysis. So if you will give a warm welcome to our speaker today. Welcome.
Thank you. Thank Professor Handico for the nice introduction. And thank you very much for your coming. It's a great pleasure for me to be here to have the opportunity to share some research work of my group. Before I start my topic, I would like to have a brief introduction to our State K laboratory. Our lab is State K Laboratory of Chemical Resource Engineering, and it has 56 staff and has 50 research fellows. And the research fellow comes from the multidisciplines, so including chemistry, chemical engineering, material science, and biotechnology. The major target of our lab is to promote the effective utilization of chemical resources, including inorganic resources such as lake brine and rare earths and precious metals, and phosphate-based resources and biomass resources. So the strategy we used to promote the utilization of chemical resources, including intercollection chemistry, polymerization chemistry, and process engineering. Because of the time limitation, today I would like only have give a brief introduction to the intercollection chemistry. The layered host we used for intercollection chemistry is layered double hydroxides, a class of anionic clay. In addition to the tunable metal composition, the interlayer gas could be exchanged by intercollection, so which provide opportunities to fabricate functional materials. So we start a study on the layered and intercalated materials from 1995. And in 2000 years, we discovered the molecular characteristics of intercalated structures. And from 2002, we started to fabricate advanced functional materials. And we focused on 3 scientific questions, like what can form layered structure, and how to fabricate structure, and why this structure has these properties. So to answer question 1, we propose theoretic criterion and the fabrication principles of layered structures. And to answer question 2, we developed the methodologies of the intercollection, and including nucleation, adjoint separation approach, and energy saving and emission reduction procedure, and item economic reaction and green procedures. Based on these methodologies, 6 industrial installations have been built up. And to answer question 3, we developed some functional materials with layered structures. And 5 of the layered structures we developed have been applied particularly in large scale. So they are heat retention additives in agriculture plastic film, and hydrogen-free flame retardant, and lead-free PVC thermal stabilizers, functional adsorbents to reclaim sulfur containing anions from cooking wastewater. And some examples with this kind of materials used in larger scale. And the sunscreens and other UV shielding additives. Sorry. So also in laboratory scale, we also developed some advanced materials such as functional film materials, catalytic materials, and biohybrid materials, hybrid materials. So we 2 papers published in Chemical Communication are selected as cover articles, and 1 paper in Journal of Materials Chemistry are selected cover articles, and 1 paper published in Advanced Functional Materials was selected as a frontispiece illustration article. And we were invited as volume editors of structure and bonding, and to present 3 review articles. We were invited to write 2 future articles for chemical communication, and 1 future article for catalysis servers from Israel. Today, I would like to talk in detail about some research work of myself group on layered catalytic materials. The topic is just as mentioned by Professor Honig, the intercalation of chiral ligand to make impact on transition metal asymmetric catalysis. Initial pure chiral compounds are widely used in pharmaceuticals and agricultural chemicals, fine chemicals, and specialty materials. And the demand from the pharmaceutical industry comes from the recognition that the enantiomers of a chiral compound could have dramatically different biological activities. Here are some samples for the. Here are some samples. For example, the thalidomide, the R's configuration is a drug for anti-nausea, but the S configuration could cause serious birth defects. So now the chiral APIs have switched from the previous regimens to now single enantiomers. In the growing global cell of single enantiomer compounds, more and more come from the asymmetric catalysis. So because small amount of well-designed catalyst could produce from the achiral precursors enantiomer compounds in larger quantity. For transition metal asymmetric catalyst, because of the diverse catalytic activities of metallic species and the unlimited structural variation of organic ligand, which provide enormous opportunities for asymmetric catalysis. So transition metal catalysts have made great success in a variety of asymmetric catalysis, such as catalytic asymmetric hydrogenation and asymmetric oxidation and catalytic cyclopropionation and hydroformylation. In addition to the sufficient activity and chemical selectivity, regional selectivity, and diastereomer selectivity, the asymmetric catalysts are supposed to produce desired enantiomer selectivity. So how to produce or enhance the enantiomer selectivity is a persistent effort for the design of asymmetric catalyst and remains a challenge. So in homogeneous catalytic system, the development of valid chiral ligand that provides desired steric environment is a choice. But in the heterogeneous catalytic system, in which the homogeneous catalyst is bound to the solid surface, and confinement have demonstrated the efficacy to enhance enantiomer selectivity. And a few successful examples of EE improvement have been reported by constraining chiral catalyst in rigid porous or channels of porous materials such as mesoporous silica. But because the energy difference between the R and S transition states is so small, and the interference from the host surface, such as space restriction and interaction, could impose adverse effects on the enantiomer selectivity. So the attempts at confinement are not always resultful, are not always successful, and the enantiomer selectivity was often found to reduce, despite the homogeneous catalyst had been well constrained. Few studies report the restriction of chiral catalyst in flexible space by intercolation, such as in the flexible space of LDH, and fewer observed EE improvement. So our work focused on how to enhance the enantiomer selectivity by LDH, by intercolation. So LDH could provide accessible bidimensional space, and the interlayer, the species and the population, the arrangement and orientation of the interlayer anions could be changed, tailored, and controlled. And the flexible interlayer spacing could be expanded even to delamination to obtain single nanoseed. So we propose three strategies to enhance enantiomer selectivity by intercolation. The first is direct intercolation of metal complex, and the confinement is supposed to enhance enantiomer selectivity. The other two involve the pre-intercolation of chiral ligand and in situ coordination to metal center. In the second strategy, the constrained coordination is used to make impact on the enantiomer selectivity. And the third is to use the steric synergies of LDH layers to enhance the enantiomer selectivity. So in the first strategy, with the titanium tartrate complex was first prepared and characterized. And the titanium tartrate complex was found to bear a dimeric configuration. Each titanium center is in a six-fold coordination. The coordination number is fitted as 5.3, and 2 titanium oxygen distance was resolved. And after intercalation into the interlayer region of LDH by ion exchange makes no effects on the coordination number and the average titanium oxygen distance. So we also tailored the interlayer spacing by control the charge density of the peroxide-like layer. And bi-layer arrangement is deduced from the characterizations. With the coordinated carboxylic groups are deprotonated and pointing to the peroxide-like layer. Applied in the catalytic asymmetric self-oxidation, we can see the titanium tartrate complex intercalated in the LDH interlayer provide higher EE than the complex itself or adsorbed on the LDH surface. So what causes the promotion of enantiomer selectivity? To answer this question, we performed several experiments, and we found the interlayer space can be swollen by the reaction medium to some extent. The swollen interlayer space means the catalytic reaction is allowed to be carried out in the interlayer region. But we also found that the interlayer space, the swelling of interlayer space depends on the polarity of the reaction medium. Less swelling of interlayer region gave rise to less promotion of EE. So we found the observed EE depends on the final interlayer spacing, increasing with reduced interlayer gallery height. So we also tailored the arranged the density of the interlayer spacing at the bi-dimensional arrangement, and found under the same interlayer spacing, interlayer galleries height, the bidimensional arranged density of catalytic centers makes no visible impact on the EE. So we concluded is the confinement that contributes to the enhancement of initial selectivity. So in the second strategy, we first make the intercollection of tartrate as a ligand, and then coordination to the titanium center. The tartrate is controlled as flat lying and vertical standing in the interlayer region, and after the coordination to titanium center makes no visible changes on the on the interlayer gallery height. So in the asymmetric self-oxidation, in each case, the vertical standing tartrate produce higher activity and higher in interselectivity than the flat-lying tartrate. So the higher activity is easy to understand. It results from the higher more titanium center population. But what accounts for the difference in the initial selectivity? To answer this question, we studied the coordination of titanium center and found the vertical standing tartrate is more easy to coordinate to the titanium center. For the flat-lying tartrate, it's coordinated to the titanium center in bidentate mode through by the carbon, oxygen, and titanium leakages. But for the vertical standing tartrate, it coordinates to the titanium center in multi-dentate mode by both carbon, CO titanium, carbon titanium, and alcoholic titanium leakages. So the later one is more rigid in the flat-lying tartrate. So in the asymmetric self-oxidation, the flexible coordination make no difference to the SI and RE attack of the catalyze the substrate, but the region coordination favor the RE attack. So the R configuration is favored. So we found in the second part work the orientation of interlayer target makes impact on their coordination moves to titanium center, and then on the asymmetric induction. In the third strategy, we attached the nanosheet of LDH to the chiral ligand, by which to enhance initial selectivity. The chiral ligand we used is chiral amino acids, and first amino acids were intercalated into the LDH in the layer region, and then we performed the delamination to obtain colloidal ligand. And this one is intercalated ligand. We call it as heterogeneous ligand. And we use the LDH layer attached amino acid as a ligand to the vanadium center, and used as the catalyst in the asymmetric epoxidation of allylic alcohol. And we found the attachment of LDH nanosheet could improve the EE markedly. For example, for the trans configuration, the EE is promoted from 53 to 92. And after delamination, the EE is not reduced, but the activity is increased markedly. So this figure that we can see more clearly for the colloidal ligand, the activity is higher, much higher than the intercalated ligand, and approaching the homogeneous system, but the EE kept constant in the whole reaction process. So, of course, we also expanded the amino acid to alanine and serine, and the similar results are observed. So the EE is improved. And we also expanded the catalyzed substrate to mono-substitute allylic alcohol and homo-allylic alcohol. And the EE improvement are also observed. So why nanosheet attachment could promote the initial selectivity? So we performed the DFT calculation and found actually the volume oxygen species could form hydrogen bonding with the LDH layer, but this hydrogen bonding increase the rigidity of the attachment of the structure. So in the catalysis, a new hydrogen bonding is formed, and this hydrogen bonding is stronger in the concave attack of catalyst substrate in the convex attack. So as a result, the energy difference between R and S transition states is increased from 9.5 to 14. So that accounts for the EE improvement. So we also studied the catalyst recovery and the recycle, and found for the solid ligand it's easy to recover, but for the colloidal ligand it's a a little bit hard to get the ligand recovered. So it's not a new finding, but as we know, the nanoparticle too small, so it's difficult to get recovered. So to this question, we perform the delamination in water, and to facilitate the recovery by liquid-liquid separation. And after the reaction, the catalytic center and the ligand are in the upper aqueous, and the products are in the organic phase, and the catalytic center in the water phase. So it's either to get recovered. And we found in the recycling, the yield and the initial selectivity is well preserved. So it can be fully recovered. So in this part, we have demonstrated that attachment of amino acid ligand to organic nanoseed could enhance the initial selectivity visibly. In summary, we have observed a confinement of the interlayer region of LDH and the steric synergy of LDH nanoseed as a substitute of chiral ligand. When in the next, the substitute role of nanoseed needs confirmation and in-depth study, and more catalytic reactions and chiral ligands are supposed to be studied. So finally, I would like to express my appreciation to the NSFC of China and the Ministry of Science and Technology of China for the financial support, and thanks to my students for their hard work. And thank you very much for your time and nice attention. Thank you.
Questions from the audience? Yes.
So how do you break the layers in annihilation, and how big are the nanosheet size?
In our work, the nanosheet size 2 micrometer, but the thickness is just 0.48 nanometer.
Right. Can we make them smaller, like not too much?
Yeah. So we can make it 20 nanometer to a few or 100 micrometer. We can tailor the size.
The sonication?
Sorry?
How do you do that?
Yeah, just by control the reaction. We synthesize the LDH by co-precipitation.
The question I had, which is, it's very nice because you can extend this into larger scale reactions, and so you have a substantial amount of control of the scale that you do these in. Certainly there's been some work on using proteins or enzyme active sites as systems where you can control layering. So you change the dimension of the active site. And, but this is infinitely more scalable, which is very good. Do you, when you get a percentage EE, so let's say you have a layer, would you also be getting very little selectivity on the edges of the material? So let's say you have substantial EE in the center, but maybe edge catalysis?
Yes, you have a great question. You have a good question. So I'm sorry, I delayed the slide. So we studied the distribution of the metal center. And then we found that when the metal center are distributed in the just in the center, so the E promotion is more more high. And but when the metal center is distributed in the edges and is promoted, is increased, but less. Yeah. So we also perform some gravity calculation to explain this, but because that results are not published, so I just
because then I could suggest that if you could prepare the edges in some way to provide an environment, maybe those edge effects would disappear. You would still get high values. But I don't know how one would do that, though.
It's right. Thank you.
If not, I'd like you to join me in thanking our speaker for providing an interesting interface between material science and chemical processes. Thank you very much.
Thank you.